By the way, so what are your backgrounds? Can I have a brief thought? Have anybody had have previously had in-depth courses in semiconductors, physics of semiconductors? Can I assume some background? What can I assume? Can somebody answer?
I think they're answering in the chat.
Acha, they're answering in the chat.
All of you can answer in the chat. Yeah.
Okay. Arrow. Okay. Sorry. Let me. How do I see the chat? Acha, chat I'm having. Okay. Engineering physics, MSc, MTech physics, electronics physics. All right. So basically, you have a reasonable background. I'm from ECE department. All right. Okay. So so but then there are only a few responses. I will assume some background. I will assume at least the math sort of a background for calculus. Okay. Uh, I suppose you all would know what is a vector field. I suppose you all will know what is divergence, what is curl, and stuff. But generally, in terms of physics of semiconductors, I will probably deal slowly. Okay. And in between, we will have a break. And if you feel there is a lot of redundancy and things that you have already seen and it's going slow, bear with me. Okay. We will soon cover up. And there will be places where you will see something interesting. And even if you still don't see it, let me know in the end. We will always have a catch-up session where we will, take a step further and go a little bit deeper. Okay. All right. So we are at 1:05. I think this is the right time to start. We already will have.
I think you should start. We should start,
All
right? Yeah.
So, okay. So I start.
Yeah.
Okay. I'm also able to annotate. Oops. Okay. I will not annotate unnecessarily, only if necessary. Okay, guys. First of all, thank you, Professor Rick Day, for giving me this opportunity. I am Krishna Balasubramanian. I am from the Department of Material Science and Engineering, IIT Delhi. This is my web page below. So I have previously been in the Electrical Engineering Department, MBLSI stream of Kanpur, and very recently moved to IIT Delhi. So my basic area of research is on two folds. One is the nanoscale electro-optics. I work on graphene on very important substrates like group 3,5 substrates. I will soon tell you what is group 3,5 substrates, like gallium nitride, aluminum gallium nitride, gallium arsenide, and these kind of materials. They have very interesting properties, very important novel phenomena are being observed in all these things. There is an observation of two-dimensional electron gas. We will soon see why 2D is very important. And the electron transport in these materials are particularly interesting because you can have very high mobilities. So graphene is one such area. I work on ultra-fast electron exciton dynamics in transition metal dichalcogenides, particularly MOS2. This is a plot of the exciton dynamics. Excitons are electron hole pairs. We will not go into details because these are optics, and this is particularly a course on electronics, so I don't go into optics. The third area in which I work is this, which is 2D nanoparticle plasmonics. So we work between two nanoparticles, graphene in between two nanoparticles, what sort of interesting applications of enhanced field we see and such. The other stream in which I work is in superconductivity device technology. I don't know if you guys are following the recent news on quantum computers. Most of the commercial quantum computers are based on superconductors. Take, for example, the Google, the D-Wave, Rigetti computing. All these guys work on superconductor. So superconductor is the backbone, is the silicon of quantum tech. Okay, I work on 2D material superconductor interfaces, superconductor based light emitters, and single photon detectors using superconducting nanowires. If you have any questions, any comments, or any interesting ideas on any of these things, feel free to email me. The email was given in the first slide. So now let's go to the, so this is my team in IIT Delhi, but I will not elaborate here. So let's go into the meat of today's talk. First, we will begin with the history of investigation of materials. We'll see how this field got to be developed and where we are today. Okay. The most important discovery came when we started to see electronic charge. What is charge? Right. So this is something which is still being discussed. It's a philosophical question. It is assumed to be an indivisible physical property which bears a force upon interaction with the electromagnetic field. People have found that there are two kinds of charge. One of them is positively charged, another one of being negatively charged. This is purely convention. The word electron came from the word amber, on which the charge was first developed or first observed. They started to observe this as early as 400 to 500 BC. And from 600 BC, they started to call it electrica, which is the Greek word for amber. And there are other few discoveries which says that the electron in amber can flow over distances. This is where metals were started to be used. And in 1933, almost all materials can be shown to collect electrons or charges. They were mixing between electrons and charges at that time, but typically charges are by electrons, right? We talk about the positively charged as holes in our semiconductors, but they are basically lack of electrons, right? So this was discovered in 1733. Remember, from 1400 to 1733, they were just looking at charges, how to generate them, how to see them, and such. So in 1750 comes Benjamin Franklin. He tells you that there are just two kinds of charges because of the attractive forces or the repulsive forces that exist. There are some qualities which Coulomb elaborates further. So in 1750, Benjamin Franklin just says there are two charges, not without going into details. We will see why there can be only two charges. This is very important. So if somebody asks you why can not there be third kind of charge, right? Alexandra Volta, from where volts is already there, is from 1800. So he showed that the charges can be made to flow in continuous loops. But more than that, he showed that you can generate charge and separate them as positives and negatives, hold them separated, and if you connect a wire through them, you can make them flow. This is the origin of a battery. And Michael Faraday came up in 1933 to 38, saying that there are some forces between charges. If you generate charges by application, you bring them together, there are some forces, right? So here, Coulomb comes in 1784. So here he comes up with some very important observations. First thing is he observes that there exists force between two charges, but this force is not just normal. He says the force is found to act on the line joining these charges, and they can either only act towards it or away from the charge. So there are two charges, right? X0 and X1, as we see here. The force is along the line joining these two. There are no tangential forces. That means this charge cannot move tangentially normally like this or anywhere else along the circle or something. Because of the force, it can only go towards or away. This is an experimental observation, right? Now, this observation already tells you there can be only two charges, right? Either either the charge configuration such that it is attractive, or charge configuration as if it is repulsive, right? And the fourth and the most important observation is says the force is inversely proportional to the square of the distance between the two. Now, the square of the distance and the charge, they are very similar to Newton's gravitation, right? So you should not be surprised when you already see the square. The square was already made famous by Newton, and the Coulomb also observes that such a behavior, such a characteristic is also seen in charges. Now comes Ampere, who comes up with very important equation. He says that there is force on the charge is Q, the charge times the field E. So now they have moved from the charge, from the force, to what is called as fields. Fields are very characteristics, and they are very useful to abstract the kind of sources. So let's say I have a source configuration of charges which have different shapes. Why people use fields is to forget about how the source is defined, how the charges are distributed, but only talk about a total impact of these charges. That's where field is. The field kind of abstracts the kind of configuration that the source has. You do not care whether you have a battery which is square, which is circular, right? You only talk about what is the electric field from that configuration of charge. And he comes up with this differential equation, which is very interesting. One is you have a magnetic field, which is a vector field, that is a vector force, which depends upon the spatial position and the direction. And the curl of this field tells you what is the current which is encompassed through this curl, right? Or the integral form is even more revealing. You take a closed line and then you integrate the magnetic field along this closed line. That integration of the magnetic field will tell you how much current that this closed line encloses, right? So this is this integral equation. This is a closed contour integral b dot dl along the closed line, and I enclosed. What is the current which is enclosed through this line, right? So this is where ampere comes in, and you know where amperes is used, right? In motors and all these things, where the magnetic field you call induction and such. Then comes the hero, in which he's the most glorified person in electromagnetics, James Clerk Maxwell. Arguably, but then rightly so. He comes up uh, with four equations which define almost all properties of charge carrying currents in materials, in semiconductors, in metals, and in vacuum. In vacuum, you have the electromagnetic fields, the radio that we see, the photons that we see, everything is encompassed in this Maxwell's equation. The first one, he says the divergence of the electric field is equal to the charge enclosed. So you have a charge which is in a volume. How much the field changes if you take one step away from the charge, how much the field changes is the divergence. Delta is dou by dou x. So spatially, how the field changes depends upon the intensity of charge that is there in the source. The second equation, which is still, people are still working on why this is so, the divergence of the magnetic field is zero, which tells you that you take an area. So this is an charge distribution, right? So like that, you take an area and then you look at how many north and the south poles, how many poles of magnetic fields that you have, you will see that they are always in pairs and they're always equal and opposite. So you take a sum of them, they will always be zero. So there are no magnetic monopoles that comes now because there is no divergence of the magnetic field. The third equation, a curling electric field will give you a changing magnetic field, del cross C. So your electric field starts to curl, then the magnetic field surrounding it should have a time variance. If there is a curling magnetic field, then you have a current. So this is something that you have seen in amperes, right? So he has just taken amperes and then say that if there is no magnetic field, or if there is no an electrical conductor in a curling magnetic field, you should have an alternating electric field. This is very crucial and important. So the first one is just ampere. Maxwell adds an additional component, which is mu naught epsilon naught dou E by dou T, who says that if there is a curling magnetic field, then you have an alternating electric field, right? So this already tells you the kind of fields that you will have in vacuum. And this is what electromagnetic radiations are basically. You take these two equations together, you will see that you will have if you have a field which has an electrical magnetic field oscillating in time, then it will have a velocity which is mu naught 1 by mu naught epsilon naught, which turns out to be 3 into 10 to the power of 8, which is the velocity of light. So while all these things were going on, people started to study about how the solid state materials are formed, what are the components of this. One of the landmark experiment is J.J. Thomson's experiment, who showed, people have already seen that you can actually eject electrons if you apply large enough potentials. So you already saw Volt say how to generate potential. You already saw how you can transfer potential by connecting metals. Now, if you have a high enough potential, then there's a large enough field. This large enough field can eject electrons. Remember, till now, they don't know why electrons are being ejected, right? But then you have a large enough field, then the electrons get ejected, right? They do not know how the atomic orbitals are, how much potential you should have to eject an electron and such. But if you apply a high enough potential, electron gets ejected. That much is known. So you have something like this. You have a cathode and anode. You have high enough potential. Electron is ejected. The electron is going through this line. Now, what Thomson did is he had perpendicular electrical and magnetic field. So you have an electric field which is perpendicular to this line, and you have a magnetic field which is perpendicular to this electric field. So he can now move this up and down and towards and away from the screen, right? And if you work around with these forces such that the electron lines do not really change and is exactly flat, which can be seen, right? You keep an eye here and then see where the electron comes. It's coming in the straight line, then you mean that there is no net force on the electron stream. If that is the case, then you know what is the velocity of the electron, right? You put this equation to be 0, the ratio of electric to the magnetic field will give you the velocity. And this curl will turn out to be just the same because the velocity of the electron and the magnetic field are perpendicular, right? So this is just V into P. So you will know what is the velocity if it is exactly straight. Now you know the velocity, you just turn off probably the magnetic field. So what will happen? There is still the electric field which is active. Now it will make the electron lines to curl or bend. And if it bends, if the bend is not too large, if the distance is not too large, the bend can be taken to be almost like a straight line. You see where it hits, you know how much vertically it has moved. Then this y of t is half at square. This is Newton's laws, right? Y is ut plus half at square. You guys must have seen this before. It is taken, u is taken to be 0 because there is no velocity perpendicular to this, right? So ut u is 0, so half at square. Now you know what is, so a from here is e is the force by the mass. You put that through this. You know what is the time because you know the velocity. You know the distance between this point to this point. So you know what is the time that the electron takes from here to here. Once the time is known, the force is known. The only thing which is unknown is E by m, and that's what Thomson determined, that he had E by m. But from here, he made this prophecy. He thought the atom should be something like this, that you have a lot of electrons because you know the electrons can be ejected or they should be independent particles. But the positive charge in the atom he thought to be distributed completely, continuously. So now comes Millikan, who showed that you can actually accurately calculate the electronic charge. I will not go into the details. This is a very interesting experiment which you can probably read elsewhere, because for the lack of time, I will just rush through here. So what he did was he took an oil drop, he passed X-rays. Actually, he passed gamma rays because he was able to get it out of a radioactive material, charge it. As it comes down, there are two forces. One is the viscous force, another one is gravity. Now, uh, because of these two forces, if you apply an electric field, because of these two forces, you can cancel this force and then this guy will drop down with a constant velocity. Now, once the velocity is known, you can calculate what is the radius of the particle and such. And now it comes to these two plates where you can apply an electric field. So the oil drop starts coming from the top. It is charged. It comes down here. Here, he applies an electric field such that he will arrest the motion. So the oil drop is no longer falling. So the electric field should now be equal to the force of gravity, right? That is the only two forces which are acting. Now, because it is arrested, there is no viscous drag. Now, with this, you can actually calculate what is the exact electronic charge. It was calculated to about 10 to the power minus 24 Coulomb accuracy, an insanely large accuracy to measure the electronic charge. So once the charge is known, E by m is known, Rutherford comes with an experiment to show that the atom does not necessarily have to have a distributed charge cloud. Why? Because when he saw this experiment, everybody reads this, right? I think you should read this description, which is very interesting, which was written in 1908. You should see the clarity in his thoughts. So he has this gold foil, he comes and then he says, a few of them get scattered to a large angles. Now you ask this question, okay, fine, it scatters to a large angle. Why should it negate the fact that you can have distributed charge? right? Why should you have concentrated positive charge just because you have scattering which is large angles, right? So I think there will be a I think these are recorded. You should go and read this description. I will not explain the answer here, but I would really like you guys to go and read this description. It's a beautifully written explanation. So from there on, there are other landmark experiments. One is the photoelectric experiments, for which the Einstein got the Nobel Prize. He did not do the experiment; he just explained it. But even before that, Fleming had been working on vacuum rectifiers. These are all very important because by then, 1880 to 1900, Morse code have been invented. People have already been talking about radio waves. Our own Bose demonstrated radio communications, and it was useful for the war. 1912, we had the war, right? 1920, 1912. So during that, the radio communication was really important. So they were actually doing those things. Now, can you think about why this vacuum tube will rectify? Why it will pass current only through one direction, not to the other? I think you guys have to think about it. It's very interesting. It has to do with special treatment on one side. They will heat one of the electrode. Because only one of the electrode is heated, there will be ejection of electron only in one electrode, not in the other way around. That is why these guys rectify. The interesting experiment in photoelectric, which was troubling people, is we have a situation like this, right? You have a cathode, you have an anode, you have a potential, and you start increasing the potential. It will, when there is no photon, your current will start increasing after some V naught, right? Now you shine a light on this one of these electrodes, and you will see that the V naught shifts. What is important here is how much ever I change the intensity of this light, this V naught will not shift any further. Why? For shifting the V naught further, I have to change the color of the light and not how much of the intensity. I cannot just turn on the knob of intensity and then change this V naught. This was a question which was very hard, which is unanswerable. And that's when Einstein said, no, that's because the photons comes in pockets, and each pockets have energies, and you have to transfer the energy from the photon to an electron here to come out. It does not matter, you can send in millions of low energy packets, it will not have enough energy to eject an electron out of the electrode to go and contribute to current. That's why intensity does not shift V naught, only the energy of the photon shifts V naught. There are other issues, right? One, atomic lines of gases. Uh, so here you see the Planck's radiation. You take a material, you heat it up to a particular temperature, your radiations are continuous. But you take an atomic gas, the radiations are not continuous. You get discrete lines. Why? Because the atom does not have continuous density of states. These things were still not known then, right? So you see discrete lines of electrons jumping from each of these atomic levels. There is another issue with the black body radiation, which is called as ultraviolet catastrophe. The classical theory of black body radiation was given by Rayleigh Jean, who said that the intensity of light at any particular temperature of any particular wavelength depends directly on the temperature and inversely to the power of 4 of the wavelength. At the same wavelength, you increase the temperature, the black body radiation intensity increases, right? It can be seen. Take a wavelength, let's say 2 microns, increase the temperature, the intensity, spectral intensity increases. But if you reduce at the same temperature, if you reduce the wavelength or increasing energy, right, you comes down, then the classical theory predicts that the spectral radiance should explode because it is power 4 in the denominator, right? But then in experiments, it does not happen. You have what is called as the ultraviolet catastrophe, which says the spectral radiance drops in the ultraviolet or the high energy or the low wavelength radiations. Why? Again, a very difficult question. And in that time when Planck gave this weird particle law, he says, oh, the photons are no longer waves, they are particles. They come up with the known energy of and then he gave them a unit of this discreteness, which is h, which is called the Planck's constant, as we all know. Then he came up with this equation, you can clearly see when the lambda becomes small, the wavelength is small. Now this is small, this exponent will break, will blow, and now you have a denominator which grows, right? So what happens? Your spectral radiance now drops. Even if lambda is small, this exponent grows much faster than the lambda, right? So your spectral radiance will now drop. So this is the mathematical equation that the Planck gave, but the exact reason for this, I have to wait for another 20 years for people to really figure out how quantum mechanics works. Niels Bohr came in 1913, who says that the uh, uh, the atom will have discrete energy levels in which the electrons lie, and when the electron jumps from one of these levels to the other guy, now there is photon which is emitted. This is the reason for having discrete lines in the atomic spectrum. And he gave an expression for the energy of these levels. I'm not going into the details of this, but then the energy was inverse of n square. De Broglie came up with a very important uh, observation. Okay, so there was no. So he said that all particles should behave like a wave, and the wavelength depends upon the velocity of the particle. So he gave this expression, which has relativistic corrections as well, but we can actually ignore this if the velocity is small enough. So the lambda is the wavelength of the particle, which is h by p. H is a Planck's constant, already introduced by Planck. P is the momentum, right? So h by mv. And it is easily understandable from the from the Bohr's model, right? So what it says is an electron is a wave whose wavelength should wrap up and come back to the same area, right? So let's say the wave has a trough here. It goes around this nucleus, comes back, it should again have a trough, right? It cannot have a hill. So if it has, then there is a problem, right? So then there is an oscillation. So if you do this, so basically 2 pi r is the circumference of one circle. 2 pi r should be n times an integer times the wavelength. It does not have to be one wavelength. It can have multiple wavelengths, but it should be an integer multiple of the wavelength, right? So n lambda should be 2 pi into r. Now, if we lose the relativistic corrections, you can say lambda is just h by mb. So you put n h by mb is 2 pi r. Bring the 2 pi down, you get nh by 2 pi, which is nh cross. This is what we all use in the physics nomenclature, right? mv into r. mv is a linear momentum and r is the radius. Linear momentum into the radius is the angular momentum. So the angular momentum is nh cross, which is already quantized, right? So this is what is the repercussions of de Broglie's statement saying that with every particle moving with a velocity v, you can associate a wavelength. During this time, there are a bunch of electrical components which were also demonstrated. You have Leiden's jar, which is capacitor. You have the Faraday's motor, which is an inductor. You have the Morse codes and the electromagnetic radiation. So people already know how to do RC circuit, LRC, RL, RL and C, how to have resonances and so on and so forth. So people have moved very quickly between, let's say in 100 years, they took about 300 years to do from charge to here, but from here they moved very quickly to electromagnetic radiations, to communications and so on. And of course, we moved even rapidly after finding the transistors, but this is also a very rapid movement. So now let's come back to our topic of interest, which is conduction. We will first see the metals, which is the most easily known, and then we go to semiconductors. We will see why this is different, and we will talk about the density of states, effective mass, doping in semiconductors, and such. So at this point, I would like to stop and ask for any questions. Are there any questions? Feel free. It has been very informal till now, so I have been just talking. So it's just local chat, right? It has never. It was not any technical till now.
Hello. Hello.
Yeah.
So very good afternoon, sir.
Hey, good afternoon.
It's a very interesting talk.
Yeah.
I'm very happy with your introduction regarding the physics of semiconductor devices. We have well introduced about Maxwell's equations also. So I have one query in Maxwell's equation, second equation in table. Why del dot B is 0? Can you explain?
So this is okay. So
Yeah.
okay. See, when you see, these are all experimental observations. Okay. So you can get down to prove Maxwell's equations, which is hard, but these are all taken. So can you prove Newton's equations?
No.
Y is F is equal to ma.
No.
Okay, so basically, I mean, you can get to the proof of it, but it is not trivial. But the reason why the divergence of a magnetic field is 0 is because you do not have any magnetic monopoles. So basically you have, let's say, a magnetic monopole in one region, only one magnetic monopole in one region, right? Then the magnetic field will start reducing as you step one step, right, away from this magnetic field, magnetic source. So then you will see what we see for charge. Why there is a divergence for charge? You let's say you take a distribution of charge density and then start stepping away from this charge density, right? The Coulomb force reduces by 1 by r square, right? So as you move away from the charge, now your total electric field will drop. Now the same is not true for magnetic field because you do not have an isolated magnetic charge. You only have pairs. They always come in pairs. Rho is an electric charge density. If you have a rho for a magnetic charge density, it is always 0. That is the reason why the divergence of the magnetic field is always 0. It comes because you do not have a magnetic charge density.
Hello, sir.
Yeah.
Is there any magnetic monopole exist in universe?
You should ask P.A.M. Dirac. You know him?
I think if any magnetic monopole exists, so this equation may not be 0. I thought.
Yeah, right.
It's correct.
So
it is correct.
You are right. If you can find a magnetic monopole, then there is a lot of problem.
Yeah. Generally, in universe it does not exist. But if any magnetic monopole exists, then it is not 0. Maybe I thought that.
Yeah, you are right. So we don't know. People are still investigating if they can find a magnetic monopole. If you can find it, you get a Nobel Prize also along with it.
Yeah, that's why I thought that.
But then you also break a lot of physics, which has already been proven right.
Yes.
So these electromagnetic Maxwell equations have been proven right time and again using in several experiments.
Okay.
It is true in relativistic field. It is true in all sorts of fields. So if we are going to say that it does not, then there can be a very small variation in this. So I don't know. All right. So okay. So maybe let me.
Sorry to interrupt. Go ahead.
No. Thank you. So it was nice. It was a nice detour. All right. So let me. Okay. So we were here. So till now we had the background. Now we go to conduction in metals. Okay, and how did people come around with understanding the conduction in metals, and then we go ahead and then see how did they start to understand other kind of materials like semiconductors, insulators, and such. So this is an experimental plot of thermal conductivity versus electrical conductivity, right? What is very surprising here is many materials fall on this line or very close to this line. You don't see.
Dr. Krishna.
Yeah.
Yeah, we are not able to see your slides.
You are not seeing my slide?
Yeah.
No, it is visible.
It is visible. I can see it.
Okay, wait.
Okay. Fine.
Wait, okay. The guy who is not able to see, so then maybe you just log out and log in, man. Sometimes Zoom can misbehave. Others are able to see?
Yes, sir, we can
Yes,
see.
sir. Yes, sir.
Yes, sir.
Awesome,
Yes,
awesome.
Yes,
sir.
sir,
It's
we can
visible.
see.
Okay, so let's go. Let's go. That the guy who has difficulty, please log out and log in. Okay, so you might be able to see. All right, so let's continue. So when you plot the thermal conductivity versus electrical conductivity, you see materials on this line which says copper-based alloys which have high electrical conductivity, who has a x-axis high, also has y-axis high. You do not or very rarely have materials whose electrical conductivity is very high and thermal conductivity very low. Why is it so? Most of the metals have common properties. They are malleable, which means that you can draw them uh, yeah, you can draw them, wait, ductility and malleability, whatever. So malleable and ductile, so which means that you can draw wires and beat them into sheets, right? Second, they are all very shiny optically. They are good electrical conductors. They are good thermal conductors. They can undergo large electric deformations, elastic deformations, which means that you can deform and again get it back. Most of them are eager to lose electrons. They very quickly like to form oxides. Oxygen is an electron grabber, right? And the ratio of thermal to electrical conductivity falls on this straight line. These are all questions which are things which and physical theory to explain conduction in metals should explain. The ratio is called as Lorentz constant, which is 2.45 into 10 power minus 8. Can people who does not want to talk put themselves on mute? All right. So let's continue. So to understand the conduction in metals, you go through what is called as the kinetic theory of electrons. I'm going to get out of this. Uh, okay. Okay. Now I'm good. So we go into this kinetic theory of electrons, which was given by Drew. He had some assumption. One is metals have large number of atoms. The valence electrons in a metal or in a material, only those contribute to conduction. There is no reasoning given yet. Okay, see, these are all assumptions which they have some reasoning from the chemical bonding kind of a picture, but generally the picture of the atomic model is yet not there. All the atoms and electrons are identical. You cannot distinguish one from the other because there are a large number of atoms and the conducting electrons. And the electron density is so large that you can treat them statistically. So you know only about the macroscopic property. You don't want to care about how each one of them move. These are all borrowed from the kinetic theory of gases, thermodynamics. This is what people do in thermodynamics. So here, now there are a lot of things which are borrowed, right? The average energy is given by half mv square. This is the average energy. This is the average energy, average velocity v in these braces. In quantum mechanics, you call it expectation value, or it's also an average value. If you use probability theory, they are one and the same. The average energy of an electron, this comes from the equipartition theorem, is 3 by 2 kBt because you have 3 dimensions of motion. Each dimension has half kBt. This can also be proved, but then we just take it for granted here. Now you know the energy. You can calculate what is the velocity from the previous equation, right? You know energy, then the velocity is just rearrangement of this. Number of conducting electrons, it can be taken from the Avogadro's principle, right? You have Avogadro number, Z the valency, rho m the mass density, A the atomic number. Once you have something like this, you know how many conducting electrons a material has. You know what is the velocity at which they move, right? With all these assumptions, there are further assumptions. There are like another 5 more assumptions for you to just understand how the conduction in metal happens. First, the electrons move like balls. They move in straight lines. They are treated as classical particles unless they are acted upon by electromagnetic forces. If there is a force, then they act like according to Newton's law, right? Once you know the force, you know what is the acceleration and stuff. And the force, you know, of the Lorentz equation, right? So you have Q times the electric field E plus V cross B will give you the total force on the material. If there are electromagnetic force, you have Newton's and Lorentz forces to contribute. The electrons do not interact with each other. This is called an independent electron approximation. So what they mean is the electrons do not repel each other by Coulomb force. Two electrons come close by, they do not interact any other way other than just from their initial momentum. The electron collides of ions in the solid and do not collide with each other. This is a slight deviation from the classical kinetic theory of gases situation. The kinetic theory of gases, the gas molecules collide with each other and then they have an average velocity. So here, the electrons do not collide with each other, they collide with ions. The ions are static particles, right? And the collisions are instantaneous. So what they mean is you have an electron which is coming, you have an ion which is sitting, they collide, and it collides and the velocity changes, right? And the velocity do not slowly increase to the final velocity value. The velocity immediately changes to the next value, right? So there is no, the transition is. These are the assumptions of Drude. With these assumptions, let's see how you can calculate what is the resistivity, how the current conduction through this. The first question is, what is the probability of collision? You take a time dt, the probability of collision is taken to be dt by tau, which is understandable. Tau is some variable for now. You can take that as a variable. As time increases, you are sure that the probability it will undergo a collision, right? If the time is small, the probability is small. So it has to be directly proportional to the time in which we are considering. So the probability to collide in time dt is directly proportional to something. So you take dt by tau, which is just a proportionality constant, right? Once this is assumed, it can be proven that you take a random electron, right? Something which a lot of electrons are going, you take a pick one electron at a time, and then you say, what is the average time it will take for it to collide next, right? Which will be about tau seconds. I will not prove this here, which is not very difficult. Once you know the probability distribution, the average time for collision can be easily calculated. It will come out to be tau seconds. The electrons achieve thermal equilibrium only via collisions. There are no other processes. All of them reach a particular temperature, a particular velocity, just via collisions. If P of t is the momentum of the electron at any time, you take an electron, it has a known mass, you know the velocity. Now the momentum will be times v, right? And it has, so let's say that P of t is the momentum of an electron at any time t. The electron will suffer a collision in next time dt with the probability dt by tau. That's what we saw previously, right? If this is the probability for it to get collided, what is the probability that it does not collide? Probability is conserved, right? If this is dt by tau, the other one is 1 minus dt by tau. Total probability should always be 1, which is known. So the probability that the electron does not collide turns out to be 1 minus dt by tau. The electron momentum at any time t, is p of t. At time t plus dt is p of t plus dt is the probability that it did not collide, and p of t is the momentum at which it started plus anything which adds on to the momentum, right? So the force. Why this is true? It comes from Newton. What is force? Derivative of momentum, right? F is dp by dt. So dp is f dt. So p of t plus dp, which is f into dt. Once this is given, you just expand this, and then if you take dt to be very small, you can neglect this. You come up with what is called as an equation of motion. This is the classical treatment. Take whichever problem you have to determine what is the equation of motion. This is what you do when you take Newtonian mechanics, you take Lagrangian mechanics, you take Hamiltonian mechanics, whatever you take, you derive the equation of motion. Once the equation of motion is known, for whatever be the force, you can calculate how the system will evolve. So this is the kingpin. You calculate what is the equation of motion. The equation of motion for this classically turns out to be dp by dt is minus p of t by tau plus f. Let's take a minute to understand this. This can be easily written from the Newton's law itself without having to go through this derivation. So dp by dt is f, which is the normal Newton's law. But you add to that something which changes, right? So what we say is, if something collides, the momentum just reduces proportional to the actual momentum that it has. So what we mean, we have an electron which is going very fast, right? So if P is very large, the change in momentum due to a collision is proportional to the velocity. If the velocity is very large, the momentum degrades very large. If the velocity is very small, the momentum degrades small. So this is what the equation of motion tells you. This is, you can come about it in a different way as well, but okay, so maybe I'll take a detour. I like to explain this. Okay, I'm going to use a pen. Oh, this is so hard. Okay. Okay. So I have a material like this. I apply electric field. Okay, somewhere like this. An electron here will be accelerated by this field E. You have a force which is Q times the electric field. By Newton's law, you have a force. What should happen to the velocity? Will you have a constant velocity, or will you have a velocity which increases linearly? Can somebody tell? If somebody falls down from a hill, will he fall down at a constant velocity, or will the velocity keeps increasing down?
Increasing down.
Decreasing down.
Decreasing.
There is an acceleration.
Acceleration.
If this is the case, I have a potential, I have electrons moving, right? How come V has a constant I? I is current. Current is basically Q times V, charge and velocity, right? So that means I have a force, I have a constant velocity. Why? How can Ohm's law be true? It is in direct negation of the Newton's laws, right? So it comes out because you're assuming there are collisions, and the collisions degrade the velocity such that you attain a constant velocity and not a velocity which increases due to acceleration. So I will clear all my drawing. I go back here. So now you can reconcile with this equation of motion. Okay, so once this equation of motion is given, we can put in different kinds of forces and then see what are its consequences. In the first case, I'm going to put a force which is an electric field force, which is small e times capital E. Capital E is the field, small e is the charge, right? So now I put this here. We're talking about steady state. When you have a steady state, this dp by dt is going to be 0, right? It's not going to constantly keep changing. I applied an electric field. I'm looking at what is happening. So all the time dynamics are lost. So P is just P, which comes mean of P, and dp by dt goes to 0. So the force, which is minus E into E, comes out to be P times, there is a mean from here, right? Mean momentum by tau. Now you can replace P by M into V. And what is the mean velocity? It is E, small e, capital E, tau by M. This will come out to be the mean velocity. Once you know the velocity, the current density, as we saw previously, is N, number of electrons. N into E is the total charge. And the velocity at which the total charge moves will be the total current density. So you know the velocity, you know the total charge density, you get the current. So J is Ne squared tau by M into E. This, my friend, is our Ohm's law, right? So with just the equation of motion and just 2 steps we take from there on, we get the Ohm's law. We get J equal to sigma times E. And this, if we rearrange, electric field is V by L, right? So V by L, J is I by A. So this is sigma. You can calculate, you can very quickly come to V equal to IR from here. It is all defined from the conductivity. You get resistance, resistivity from there. Okay. So we have kind of given a proof to Ohm's law with a lot of assumptions before. Now let's see if these guys make sense. So this is in a table of all the elements and their density that we know. What is its resistivity? What is the relaxation time? So we know that lithium has a density of 4.70 and per 22 centimeter cube. It has a resistivity of 8.55. I think it is 10 power minus 8 ohm centimeter or something. I don't have the numbers here, which is wrong. I'll put it in the next time. Copper, which has a higher density of electrons, have a lower resistivity. True. Silver, which has a little lower little low density of electrons, now have a lower resistivity. Why? It has to do with the relaxation time playing here, right? So now relaxation time also plays. It is just the, not just the numbers, but also the relaxation time. With all these things in place, you can kind of reconcile why metals conduct the way they do. But there are other issues. First thing is the resistivity with temperature. So what you see is, as I reduce the temperature, the resistance drops. Now, if I use the conventional or the classical theory by Drude, we cannot explain why the resistance drops and saturates at low temperatures. Why does it not keep on dropping? The same thing is observed at higher temperatures as well. So there is no linear relationship with temperature. One cannot take the equipartition theorem and then associate velocities from the equipartition theorem and then think that this is how it will behave at low temperatures. The temperature dependent resistivity of metals was a big issue to be explained by the Drude's model. The second difficulty came when you apply the magnetic field. So there is the Hall effect and such, right? So you take a material, a bar of semiconductor or a metal, you have an electric field and apply a transverse magnetic field. The transverse magnetic field will make the electrons go in circles, right? We take the same equation that we saw previously, the equation of motion, which we discussed previously. Oops. So this is the equation. So I go here, take that in the force. Now I put the Lorentz force. You have the electric field and the magnetic field. Now, because this is a cross, you have to talk about X and Y. Now you're already breaking down into at least 2 dimensions. You cannot treat things as simply as in the 1 dimension in the Drude case. You break it down. Now you have 2 equations. Once again, the dP by dt is 0 because we're talking about steady state. When we do something like this, the transverse electric field, let me draw here. I should have had an image here. So I need to draw. So I have a bar of material. I apply electric field. So there is a current. All the electrons go in this fashion. Now I apply an out of plane magnetic field. Now what does the out of plane magnetic field do? It makes the electrons to curl. Right? It depends upon the field of the magnetic field. If the field is small, the curl is large. If the field is large, it will start curling like this, much smaller, depending upon the cyclotron frequency and such. But let us say that it starts curling. Because the electron starts to curl, you will see what is called as a transverse potential. This is the Hall effect. You get EY. If there is no field, there should not be any EY. Both this line and this line should be at the same potential. Because there is a magnetic field, you start getting a transverse potential EY. And you define what is called as the Hall resistance, which is a ratio of the transverse field by the in-plane current. So you have an in-plane current Jx. There is no transverse current, by the way. You should remember that. There is no current in this direction. Ey is 0. There is only Jx. Sorry, Jy is 0. There is only Jx. And you have a Hall resistance Rh, which is Ey by Jx. What was observed experimentally was you have positive and negative Hall resistances. Both of them were observed. But if you use the Drude's model, what comes out is the Hall resistance is always negative. So from this equation, from the equation of motion that we previously described, you derive what is the Hall resistance. The Hall resistance turns out to be minus 1 by Ne. And E is electronic charge, and you know that it always is negative. And we know the E is always negative, right? You have only one charge that we talk about till now. In metals, you have just electrons. Electrons have negative charges. So the Hall resistance was always negative from the Drude's model, but experimentally you get both positive and negative. So one was not able to understand why you will have positive Hall resistances. This has to wait till you understand what is crystallinity, what is order, what is bands, what are band gaps and such. So that's where we are going at. So now we will talk about crystals and symmetry and structures for some time. And then we'll once again jump to understanding bands and band structures. Okay, so this is a small detour again from the metals that we saw. Are there any questions till now? Do you understand conduction in metals? All right. So now we understand. So we saw Drude's model. We saw what are the downsides, what Drude's model understands, what Drude's model cannot explain. Cannot explain the temperature dependence. It cannot explain positive Hall coefficients. There are other things in Drude which we are not going. Right?
Sir,
Yeah.
yeah, as you said, the silver is better conductor than copper, and its N value decreases and tau increases. That's all right. We understood, but there are some. I heard like this. There are some aluminum like that. Although what happens? This is reverse. Is it true?
No, Praveen, I'm not able to understand your question. Can you please elaborate? What are you saying?
Sir, this is means what density and n are inversely proportional normally in some matter, some cases. Means as you said in your table, sir.
Uh-huh.
And in some cases, this is also true that density is directly proportional to n. Means,
Yeah. So my friend, so look at the same table here. Okay. Yeah. So look at this. You have beryllium, okay, whose electron density is like, I don't know, 5 times copper.
Yeah.
Whose relaxation time is smaller, little bit, I mean like 4 times smaller. But the resistivity is twice larger. Why?
And everyone say, yeah, it is
exactly. This is the problem. Yeah. So Drude's model, you are right. You are on the right track. Drude's model explain a few things and cannot explain a lot of things. So for simplest materials, it explains. For beryllium, for aluminum, there are other issues for other materials in which things are not very well explained. You are right. So hold on to this thought. We will address this. Why Drude's model is not complete is also there. There is another important consequence of Drude's model which I did not go and explain completely. Acha, chalo, let me also do that. So you have this okay, this is the conductivity. Inverse of this is resistivity. Okay, so you take the measured resistivity from here. You take the relaxation time. You know the velocity of a electron, right? So because you know what is the temperature you are looking at, and once you know the temperature, all the other things are known. You know the velocity, you know the relaxation time, and you can tell what will be the characteristic length. That means after what length the electron gets scattered. That's called as the characteristic length of an electron in a material. So if you use the Drude's model, what it tells you that the electron, as it goes through the material, gets scattered at each and every ion core. The length of the length that the electron can travel without getting scattered turns out to be, even at low temperatures, turns out to be that it scatters about few tens of angstroms. So what it means is that electron can only go in straight line between atoms, and which is experimentally not shown to be true. They have shown that in pure materials, electrons can grow several microns, which means that it can go millions of atoms. It just passes through millions of atoms as if it did not see the ions itself. So these are all experimental proofs which says that The Drude's model is not completely true. It does not obey. I mean, it does not satisfy all experimental observations. There are still issues, but that's why Drude's model is rarely used, right? While, but I should not say it is rarely used. This equation is used everywhere. But the tau, which is a phenomenologically introduced thing here, the way you determine tau is very different. The way you determine tau here comes from the velocity, which comes from the energy, which comes from the equipartition theorem. But as you will soon see, the energy of the electron cannot be determined by equipartition. Anybody who has taken physics who told me they have already taken, can you tell me why?
Excuse me.
Why the energy of an electron cannot be determined by equipartition?
Equipartition.
What stops it?
Equipartitions. But energy is equally distributed through all the degrees of freedom according to equipartition theorem.
So I am saying the biggest problem lies here. The energy of an electron cannot be determined like this. You take a material at a particular temperature, you cannot say that the energy is from kBt and the velocity is such. Why?
Sorry, please explain. I am not getting.
No, it's okay. If this is what our course is for, so I will explain this answer later on. But anybody who has taken this, who feels that our whatever that we are dealing here is a little bit known, can explain. Then I will little bit polish on top of it. Or if you are okay, then I will go ahead and explain this in the flow of the lecture. Okay.
Oh, sir, go ahead.
Hi, Krishna. I think
Hi, Rick.
some of them are trying to answer in the chat.
Okay, I cannot. Okay, by the way, I cannot see the chat, so you have to speak up because I can see the chat, but already I have too many things here.
Yeah, okay, no problem.
The pen and this. So it's already
from Radhakant Das has written uncertainty principle.
Okay. Now I see. Thank you. No, Rick, you don't have to trouble yourself. Okay, it's fine.
Okay.
Radhakanta and anybody who wants to answer, please speak up. Okay, so we are. Yeah, this is an informal course, so you should speak up. But then, anyways, the uncertainty. If you say the uncertainty principle, what the answer is actually no. But why do you think uncertainty plays here?
सर्टिफिकेट ऐसे अप्लाई करो मिलेगा उर्दी मिलेगा
Okay.
अगर नाम का लिंक हो तो पटना मिल सकता
Dilip Singh, you should mute yourself. Okay, so let me continue. Okay. So the answer to, I will answer this question. What is the real difficulty with Drude's model?
What is the sample को कुछ measurement knowledge का
Huh?
और बहुत different
Rick, can you give me a host permission?
publish कर रहे हैं काम करना मिलेगा तुम्हारा प्रॉब्लम है पब्लिकेशन साथ में चलता रहना तुम खाली हो कॉल बहुत ज्यादा नहीं हम लोग सेकेंड पॉइंट देख रहे थे नौकरी मिलना बहुत मुश्किल है लेकिन हाँ हम तो आज सोच रहे थे कि क्यों ना तुम अप्लाई करो अब्रॉड भी करो और हम एक प्रोजेक्ट डाले जिसमें हर एक काम डालेंगे इसी तरह साथ में रहने का भी कोशिश करना है
तो साथ में रेस्पेक्टफुली रहने का तो यही है कि
Hey guys, please wait. I'm trying to mute this Dilip Singh.
So right hand.
Guys, please mute yourself if you are not talking here, okay? All right, so let's continue and I will explain the answer. I will explain it later on, okay? So let's go. All right, so to really understand what is the problem with Druth's model, we have to look at we have to look at
So ऊपर उठने का कोशिश करो.
okay. Thanks, Rick. Wow. All right, let's go. So, okay. So, to understand the difficulties with Druth's model and improve upon it, we need to understand crystals and we need to understand periodicity. So, we will begin with how do you get crystals in the first place? Experimentally, what crystals exist? Do we really have crystals? Do we really have periodicity? And then go ahead and see what are the consequences of having periodicity. Okay, the most simplest crystals that we see on an everyday basis are of course our semiconducting crystals. We have silicon single crystals, we have gallium nitride single crystals, we have gallium arsenide single crystals. You can see the prices also here. The silicon single crystal, a 2-inch crystal, costs about $30. A gallium nitride single crystal 2-inch is about $2,500. We all have seen gallium nitride, right? So people talk about gallium nitride crystals devices in chargers nowadays. Why? Because gallium nitride is a device which can handle high power. So people want gallium nitride single crystals for electronic devices in chargers. Tesla and other companies are using gallium nitride based devices, silicon carbide, gallium nitride. You have gallium arsenide single crystals, which are also used, which are used in high-speed electronic devices. If you are looking at oscilloscopes and such, you'll start seeing gallium arsenide, indium arsenide, and such. It's not very expensive; it's about 28. Nowadays, you have also heard about graphene. You have single-inch or 1-inch by 1-inch graphene, which comes around at $300. You know, graphene does not come as a complete wafer; it has to sit on top of somebody else, some other material. Gallium nitride epitaxial wafers are existing, which cost not $2,500 but about $500. People use mostly gallium nitride epitaxial layers. Why epitaxial layers are important, or what is epitaxial layers? We will see in soon enough. Why some materials are expensive and why some are easy or which are less expensive? It has to do with what is their melting point. Do we have a melt in the first place? You see the melting temperatures of different materials. Silicon with 1680 is a more approachable melting temperature. You take other materials, let's say beryllium oxide, zinc sulfide, you don't get single crystals. Why? Because the melting point, you see carbon, graphite, diamonds, you don't get single crystals. Silicon carbide, you don't get single crystals. Why? Because it has a very large melting temperature. It's very difficult to have a melt and then grow. And how do you grow from melt? This is the single crystal growth of silicon. People say that you get silicon from sand, but you don't really get it from sand. You need silicon which is 9 orders of magnitude pure. How do you get this? You go through this chemical process to get a very pure silicon. Once you get a very pure silicon, you put it in a crucible, you melt it, you get it to temperatures above 1600. 1500 is shown here, right? So you melt them and you insert a seed crystal. You insert an already existing single crystal silicon and you will see that the single crystal silicon grows around this seed crystal. This process is called as a Skoralski process, which is seen here. See, in the Skoralski process, you have a melt, you have a seed crystal which comes out from the top. You rotate the seed crystal and you rotate the crucible as well at a particular temperature. You have an equally distributed temperature and the velocity profile, and you get a very good single crystal silicon. This process can be used for few materials, but not for all materials, because you don't get a very good stoichiometry and the melt. For certain materials, the melt temperature is so large that you cannot work reliably. And for some materials, you don't get very good stoichiometry. For these materials, we use what is called as epitaxy. Epitaxy is a method of growing matched or defect-free atom over atom kind of an arrangement. You take a substrate. This substrate is called a single crystal, because if you translate from one point to the other point, the atom, you get the same vision. You take any point in the crystal and look around in different directions, you see the same arrangement of atoms. You call such a system as a lattice or a crystalline material. If all of them are having the same arrangement, you call it as a single crystal. Now, epitaxy is a way of growing one material on top of the other having the same arrangement. If the atomic gap between the two atoms in that material is the same, you have a matched epitaxy called as homoepitaxy. Homoepitaxy is two materials, the same material, one on top of the other. You have a matched epitaxy if you have two different materials in which the atomic separation is almost similar. If it is a little bit more different, you get what is called as a strained lattice. You see the yellow one is larger than the orange one, and the blue one is slightly smaller. In both these cases, you get a compressively strained or a tensile strained material. If the strain is relaxed, you start to have defects. You have what is called as a relaxed material. There are different ways the epitaxy can be done. One way is called the liquid phase epitaxy, where many people have already done. So you have already seen the Skoralski method. So you have a melt and you insert this single crystal substrate right below the melt. And when you have something like this, you form what is called as an alloy. And when the alloy, you reduce the temperature, it will segregate. Depending upon the percentage of each of these materials, it will solidify. So you have different melts. For instance, if you want to grow aluminum gallium arsenide on top of gallium arsenide, you have an aluminum gallium arsenide melt here. You put a gallium arsenide wafer below, and the aluminum gallium arsenide will solidify right above this. This is the way you grow liquid phase epitaxy. Another way to do it is called a vapor phase epitaxy. Instead of having a melt, you send different gases. For instance, if you want to grow gallium arsenide, you send trimethyl gallium and arsine. ASHC is arsine. If you want to grow aluminum gallium arsenide, you send trimethyl gallium, trimethyl aluminum, and arsine. Right. So you have different gases. You send them through. You maintain a particular temperature, and then you grow this material on top of the other. In vapor phase epitaxy, you have no physical contact. You can grow very thin layers. You can have sharp interfaces. And these developments have been very crucial for the state in which we are right now. This is the way in which you form what is called a two-dimensional quantum well. And this two-dimensional electron gas has been used in many places in RF devices that we talk about right now, and also in silicon. So this epitaxy, MOCVD, liquid phase epitaxy, vapor phase epitaxy, all these things are crucial for the development of electronics as we have it. So here is an example. People have grown gallium nitride, aluminum gallium nitride super lattice. It's called super lattice because you have one over the other. You have gallium nitride, aluminum gallium nitride, gallium nitride, aluminum gallium nitride, kind of a periodic lattice. People grow also silicon germanium heterojunctions. Do you know why people grow silicon germanium? Silicon germanium is a strained layer. When you have a strained layer, the mobility is different. So you can have a high mobility transistor if you have a strained silicon germanium layer. So this is used in our cell phones that we have today. Excuse me. Okay. And the last method that we will deal before we actually jump into the way in which we are going to discuss these materials is called the molecular beam epitaxy. This is one of the most complicated, but the most precise way to grow ultra thin layers of high precision quality. Is there a comment? Okay. of high precision quality. So in this, you have several sources, and each one of them give you one particular molecular layer. You grow a layer over layer over layer. You control how each of these layers are grown. You control what is the doping density. You work at ultra high vacuum, and you grow at approximately one monolayer per second. So you grow one monolayer over monolayer over monolayer. So you can get ultra high precision in your stoichiometry and very low thicknesses and very good quality. So in this technique, you also monitor the way it is grown by using what is called as an read, which is electron diffraction gun, which does crystallinity measurements using electron diffraction. We did not go into details about electron diffraction, but if necessary, you can ask me any questions that you have. All right. Apart from these 3D and 2D structures, you also have 1D nanostructures. These are carbon nanotubes. They are grown by what is called as a vapor phase epitaxy, VLS, vapor liquid solid method. You take silicon and you have a gold droplet. When you send in a carbon vapor, they send in a silicon vapor. Silicon gets absorbed in the gold, and then you grow what is called as nanowires. You can see the thing here. You can do the same thing for carbon as well. Just the same. The last kind of a structure which is seen in solid state physics is 0D structures, or the quantum dots. There are many different quantum dots: indium oxide, cadmium selenide, zinc oxide, zinc selenide, cadmium sulfide, and so on. They are grown by very simple chemical means. So basically, you have what is called as this. So you have this flask at a particular temperature, and then you have the salt, and then you have the solvent, and then you play around with the temperature. You can crystallize or nucleate nanoparticles, nanodots, and such. Each of these nanodots are used in applications like solar cells, light emitting diodes, and such. People have seen this plasmonic effects or particle related band gap effects. You see absorption at particular frequencies which are useful in surface and Raman spectroscopy, and so on and so forth. Okay, to understand all these things, one has to realize what is symmetry. So I think at this point I will stop and ask if you have any questions. Let me do this. So I will stop this this session here, and let's reconvene at 3:30.
May I ask
Yeah, go ahead.
one
Yeah,
question,
yeah, please.
sir? Sir, how quantum dot is different from one-dimensional nanomaterials?
Okay, so let me go. So this is a quantum dot, right? And this
Yes,
is
sir.
one-dimensional structure. So what is one dimension? What is two dimension? Okay, let's go one at a time. You know 3-dimension, right? So 3-dimension is you have a large, let's say our silicon wafer is 3-dimension. So this is a 3-dimensional layer. Okay, you have a large X, large Y, and significantly large Z. Correct? So this is a 3-dimensional material. What is a 2-dimensional material? So you have a quantum well here. Okay. So your gallium arsenide substrate is a 3-dimensional material. Your N gas is a 3-dimensional material. And your quantum well, this N gas, the small layer here, this is a quantum well. This is a 2-dimensional material. Why is this 2-dimension? Is because the dimension in thickness, the thickness is incredibly small, or several orders of magnitude small in comparison to the other dimensions, the X and Y. So here the X and Y can be in inches, and the thickness is in nanometers, right? So an inch is about 10 power minus 2 meters, and the thickness is 10 power minus 9. So it's 7 orders of magnitude smaller in comparison to the X and Y dimension. And that's why you call this a 2-dimensional structure. Okay. Now you understand 2-dimensional structure. Let's come to 1-dimensional. Let's talk about what is a carbon nanotube. Here, There is no x and y, you have only a radius, right? So the thickness is really, or the height is really large, but the thickness is very small. So the thickness for a carbon nanotube is about less than let's say less than a nanometer, right? 1 nanometer. But the height of this can go into several microns. So it is at least 4 orders of magnitude larger in one dimension in comparison to the other dimensions that this has. That's why it is called as one-dimensional nanostructure. Now, what is zero-dimensional structure? All the dimensions that we consider are of the same order, and they are all very small. The lateral sizes x and y and z ranges from 10 nanometers to 100 nanometers. That's why all these structures are called as 0D structures, because all the dimensions are small. Now, these are all physical aspects. Fundamentally, what is different in each one of them? For that, you'll have to wait. The answer comes in the next lecture. Did I answer you?
Thank you, sir. Thank you, sir.